Hello. So, we continue with methods for solving things. So, and the place where I stopped last time was a kind of right place to stop, because such an important topic as linear equations deserves to happen at the beginning of a lecture. Right, so let's see. So linear equations, which I have defined for you already, they are what they sound like. They are equations that are linear. Have a bit of a special status, because actually, if you take a nonlinear equation and look at it in the vicinity of some place, you can always expand the nonlinear function that specifies the equation around that place and turn the equation into a linear equation. So this is called linearizing. So actually, locally, locally all ordinary differential equations are linear if you're sufficiently close to some point. So that's clearly important. So we'll spend quite a lot of time on them in this course. Actually, the majority of the course is about linear equations, partly because of this importance of theirs, and partly because those are the only ones we know how to solve, really. Right? Except in 1D. In 1D, you saw that we can do quite well on integrating equations, but it turns out that as you go to second-order equations, for example, linear is almost the only thing you can do, and actually not even all linear equations we know how to solve properly. So let's have a preview of what we're going to learn about linear equations by looking at the first-order linear equation, the simplest of them all. So I'll use t as a variable for a change. So y dot is equal to some function a of t times y plus some function f of t. And the Cauchy problem for it, meaning the initial value problem, will formulate as y at time 0 is equal to some place. You might be wondering, oh God, what will this hold for initial condition set not at time 0? And my answer to you is define as 0 the time at which the initial condition is set. So we do this, and so I'll solve it to you in two different ways, basically by way of an example. This is a kind of example, right? If instead of a of t I put 7, this would count as an example, right? So first I can show you how to solve this by a method that I referred to in general in my previous lecture, but for which I didn't give you an example. Although I have since put in an example into the notes, so keep track of the latest versions. So so how do we solve this by an integrating factor? Well, first you want to turn this equation into equation in symmetric form, which means in differentials, right? So which means just multiply by dt on both sides. So then this equation becomes dy equals to a of t y plus f of t dt. And you see that this is not obviously separable, right? If I divide it through by the square bracket, this wouldn't help because there's a t and a y mixed up here, right? This is also not, actually this is obviously not an equation in full differentials either, right? Because d by dx of 1, this is multiplying 1, d by dx of 1 is not equal to d by dy of this, generally speaking, right? Unless, of course, a is 1. Okay, but let's ask whether we could multiply both sides by an integrating factor, which I call lambda, and make it into an equation in full differentials. And I will look for lambda in the form of being a function only of t, but not of y. I wish to do it this way, and if I succeed, then nobody can judge me, right? So that's the principle of looking for integrating factors. So what do we need? We need d by dt of this. So d lambda by d. Well, actually, since I'm looking, since lambda is not a function of anything else, it's just d by dt of this. So lambda dot, right, has to be equal to d by dy of this. Well, d by dy of this is a lambda. Right, so that's what needs to happen. Sorry, with a minus, isn't there? There has to be a minus. Oh, what have I done? Yes, actually, there has to be a minus. That's right. So remember, it's sorry. It's p dx plus q dy equals to 0, and we need dp by dy equals to dq by dx. But here, the equivalent of one of these things is with a minus because it's on the other side of the equality. So this has to be a minus. You'll see in a moment that this works, but I needed to check. So, right. So this is the equation for the integrating factor. That's easy to solve, right? How do we solve it? Well, we solve it in the usual way. Integral of d lambda over lambda is equal to minus a dt. When I integrate this, I get log lambda equals to, well, again, minus integral of a dt. And I don't actually care about constants here because, remember, integrating factor doesn't need to be general. So I will choose my constants in the following way. I will integrate from 0 to t and call this t prime. Okay? So that means lambda is e to the minus integral from 0 to t dt prime at prime. So that's my function. Now I need to multiply that equation by lambda and show that that I can actually integrate something this way. So what do I want to do? I want to say lambda y dot is equal to a lambda y plus f lambda. Right? Well, what I now want to do is I want to say that this lambda y dot is d by dt of lambda y minus y d lambda by dt. Right? And then this minus y d lambda by dt, because lambda satisfies lambda dot equals to minus a lambda, is actually a y lambda. And so this cancels with this, as it should. And we end up with an equation that looks like this. D by dt lambda y equals to f lambda. And this is now separable. Right? In fact, it's not just separable. We can just integrate it directly. Right? So lambda of t, y of t, is going to be an integral dt prime lambda of t prime f of t prime. I can integrate up to t from 0 and add a constant. Finally, the solution y of t is 1 over lambda of t integral from 0 to t dt prime lambda t prime f of t prime plus a constant. Okay? And furthermore, if I want to solve Cauchy's problem, well, y of 0 is equal to what? This will be 0 at y of 0. Lambda of 0, the way I have chosen, is 1. So y of 0 is c. And that's y naught, and that's what goes into the constant. So I've solved the problem completely. Let's write the solution in a final form. It's y naught times 1 over lambda, which is e to the power of 0 to t dt prime at prime, plus, and here I have an integral from 0 to t dt prime, f of t prime, and there I have lambda of t prime divided by lambda of t, and lambda is that exponential over there. So I can write the result as e from t prime to t double prime a of t double prime. So this is the solution of the linear equation. So this is one way to solve it. There is another way of solving it, which I prefer, actually, and which will be actually the one that will be most generalizable to multiple dimensions and so on. So, but this is just a useful example of how you use an integrating factor. Okay? So this is called solution via the method of variation of constants. So here's the other way to obtain this result. So remember, the equation is at the top of the board, right? So what I'm now going to do is I'm going to write an associated homogeneous equation for this problem, right? In other words, I will first consider y dot equals to ay, okay, for now. And try to solve that first. You'll see in a moment why that's useful. So homogeneous equation, I remind you, is an equation without the freely hanging force, that F, right? And the reason it's called homogeneous is because scaling y on both sides returns the equation to the same form. So, well, this equation, unlike the linear equation from which I got it, the inhomogeneous equation, is separable, right? This is just dy over y equals to at dt, right? That's what it is, and then I can integrate it. When I integrate it, what do I get? I get y of t, log y of t, equals to integral, and again, let me integrate from 0 to t, dt prime at prime plus c. Now I can exponentiate this, and this gives me yt. I will rename e to the c, and so c e from 0 to t dt prime a of t prime. Now, let me, in order to save myself writing of algebra, let me call this e of t, this function, a kind of generalized exponential with a instead of time, with the integral of a instead of time. So the method for solving linear equations, this was invented by Lagrange. So Lagrange is one of these people who give hope to immigrant foreigners like me. You know, he was called Giuseppe Lodovico Lagrange, and he was an Italian immigrant in France. Became Joseph Louis Lagrange, senator and count of the Napoleonic Empire. So you can see what my ambitions are, right? The British Empire is getting restored next year, right? You know, I do have hope. You know. So. They will need a viceroy of Jersey or something like that, right? So mathematicians can advance, and maybe physicists too, who knows, right? Anyway, Lagrange's method for doing this. So what Lagrange suggested was let's turn the constant that's in front of this solution into a function, just formally. Replace c by psi of t. You like Greek letters, right? So, let's do that, and let's look for a solution. Look for solution of the inhomogeneous equation in the form y of t equals to psi of t times this e of t, the solution of the homogeneous equation. Let's see if this works. Right? So we now have a full equation, which is y dot equals to ay plus f. And I take this and I substitute into it. So what do I get? Y dot is equal to psi dot e plus psi e dot. And that has to be equal to a psi e plus f. Okay? But this thing here was a solution of the homogeneous equation, right? Which means this is equal to a times e. Verify, take e and differentiate with respect to time. That's what you will get. Well, hurrah, these two cancel. And so I get psi dot equals to f of t divided by e of t, which I can integrate. Psi, therefore, is constant plus integral, say, from 0 to t dt prime f of t prime e of t prime. And so success, I have y of t is equal to this psi or psi times e of t. So e of t times c plus integral from 0 to t dt prime f of t prime e of t prime. Of course, you must have noticed by now that e of t is 1 over what I previously called lambda of t. 1 over the integrating factor, if you like, an integrating divider, rather than a factor. So, well, the initial condition, y of 0, well, e of 0 is 1. This is 0, so y of 0 is again c, and that's y naught, and that's what we put in there, right? And so we've got a solution which is the same solution as I obtained before. Incidentally, you might say, well, how can we just look for a solution in some form, right? And then get this and expect that this is going to be general, right? Well, we expect this on the basis of the existence and uniqueness theorem. Existence actually doesn't enter into this because you have produced a solution, so clearly it exists, right? But the uniqueness is important. If I have produced a solution to Cauchy problem, then it's the solution to Cauchy problem, right? So you can actually, you can stare at an equation, have a moment of mathematical epiphany, write down the solution without explaining anything. If it's the right solution, it's the solution, right? And technically, we can't question you for how you got it. I mean, for the purposes of declaring you a winner, for the purposes of testing your ability to explain things, we can. So, Right. So there's one more important thing that I want to emphasize about this solution to a linear equation and the method by which we have got to it. So notice that what is the structure of this solution? So the structure of this solution is it's the solution of the homogeneous equation. Look, C times E of t, right? That was the solution of the homogeneous equation. In the nomenclature of differential equations, this is sometimes called the complementary function. Complementary function, not complementary function. Okay? This function flatters nobody, but it complements things. And then plus that other bit, right? And the second bit it had two features. One was that this second bit is the solution of the inhomogeneous, is a solution, sorry, of the inhomogeneous equation, right? Without that C could be 0, for example, right? This would be a solution to the homogeneous equation, right? And it has no constants in it. So it's a particular solution of the homogeneous equation. So this, again, in this business is called a particular integral. Which leads us to in a sense, a third method for solving the linear equations. The method is this: solve the homogeneous equation first, then find any solution, some solution of the inhomogeneous equation, doesn't matter which, add them together, and that's the general solution. Right? Now, why might you say, how is this possible? This is clearly not unique. Right? Well, you can show, I'll leave this to you as an exercise, well, I will show it again in many, many times, but in this case, I'll leave this to you as an exercise. You can show that if I use one particular integral or another, the difference between the two is always going to be a solution to the homogeneous equation. Well, the way you show it is by just subtracting the equation with one solution from the equation to another solution and realizing that the difference between any two particular solutions of the inhomogeneous equation is a solution of the homogeneous equation, which we have here in the general form, which means any non-uniqueness here will be absorbed by the constants inside there, by the constant inside there. Okay? So, and again, the reason you can do that, the reason you can choose just any particular integral and add the homogeneous solution, is because in the end, the solution to the Cauchy problem is unique, and so if you can find it, then all is well. All right. So that's your introduction to linear equations. We'll return to them shortly, but let me do a few more things first. So another equation, not linear, which is known how to solve, is the equation due to Jacob Bernoulli. We have to say Jacob Bernoulli because there were 8 of them. There were 8 Bernoullis in that family: brothers, children, nephews. Basically, the whole clan was doing mathematics. And they all did important things. And so when you say Bernoulli is this or that, you're actually referring to a whole collective. So, so Jacob Bernoulli was, I think, the most important of them. I think he was like the pater familias or something like this. He was a student of Leibniz, and they fought Newton together. And then his brother was the advisor of Euler. See, they all knew each other in those days, right? It's sitting here in Oxbridge, you think, oh, it's scandalous, right? This small mathematical elite, all supervising each other, and probably giving each other jobs, brothers, sons and so on, not sisters in those days, alas. Right. So Jacob Bernoulli came up with this equation. Y prime plus A of x times y equals to B of x y to the n. Okay. So, I should, another interesting factoid. He discovered E. Remember we talked about E to the x? So E is due to Jacob Bernoulli. So now, what about, well, this equation is clearly not linear, right? It's not linear provided n is not equal to 0 or 1. If n is equal to 0 or 1, you already know how to solve it. I've just told you, right? So now, if n is larger than 1, well, firstly, y equals to 0 is clearly a solution. But such solutions tend to be not very interesting. So now, let's put it to one side. Let's say y is not 0. Let y not be 0. And then divide by it. So if I divide by y, I divide by y to the n. That's what I want to do. So I want to take this equation and divide it by y to the n. Then I get b of x minus a of x y to the power 1 minus n equals to y prime divided by y of n. But y prime divided by y of n is d by dx y to the 1 minus n divided by 1 minus n. Check. Right? This is easy to see. Well, now, let z be y 1 minus n, a new function. Okay? And you can see that if I do that, the equation turns into d by dx of z equals, well, plus 1 minus n times a of x z equals to 1 minus n b of x. And this equation is linear. And so I have just told you how to solve it. Solve by standard operating procedure. Okay? So that's one nonlinear equation that has consequences. Here's another one. This is going to be the last one in this set, because basically this last equation is both a success and a failure, right? So this equation is called Riccati equation. Riccati was also called Jacob, as Bernoulli, and did absolutely nothing else besides discovering this equation. So he's a monumentally undistinguished man. He lived in Venice and was a lawyer, so he did have a good life. So so this is, maybe I should turn this around and make it positive, right? Those of you who are going to go on to be a lawyer and live in Venice should not feel in any way inferior to those of you who will become mathematicians and receive Fields medals, or produce 8 children and appoint them all to professorships. So there are many ways to succeed in life, open to Oxford students. The equation is this: y prime, equals to a of x y squared plus b of x y plus c of x. Okay. So firstly, what's the failure? It turns out that equations in this form are generally impossible to solve in quadratures, right? When you, generally speaking, come across an equation like this in your studies, so y prime equals to a linear bit plus a quadratic bit, right? This is the point when you throw your hands in the air and say, that's it. I can't. It's a Riccati equation. Nothing to be done, right? So become a lawyer, move to Venice. That's it. But there is a loophole which allows you to stay in Britain and be a mathematician, right? And the loophole is this. Suppose, so generally speaking, I can't solve it. But let's say I have looked at this equation and intuited a particular solution of it. Right? I can just see that there is a solution to it, right? And that solution happens to be, suppose y naught of x is a solution. Generally speaking, having a solution of a differential equation is not particularly useful because it's one out of a set of an infinite number of them, right? So, and this equation is not linear, so you can't simply multiply it by a constant and get the whole lot, right? So, so let's say you have so then the prescription is that seek solution to that equation in the form y equals to the solution you have guessed plus the rest. And let's see what equation is satisfied by the rest. Well, let's see. Y prime is equal to y naught prime plus z prime. And on the other hand, I can substitute it in there, right? So it's az squared plus 2a y naught z plus a y naught squared plus bz plus b y naught plus c. Right? That's what I have. But y naught is a solution of the equation, and therefore y naught prime must be equal to a y naught squared plus b y naught plus c. And therefore this cancels, and this cancels. And so therefore z prime is equal to, what's it equal to? Well, there are two linear terms here, so 2a y naught plus b times z plus a z squared. But that's a Bernoulli equation. Okay? Look, just like that one. So a Bernoulli equation, and therefore reducible to linear, and therefore solvable. Okay? So that's that. That's the last type of equation that I want you to know how to solve. So you have amongst the non-minimal questions in your homework, there are two examples of Riccati equation that you can play around with. You might say, how does one ever guess a solution? Well, sometimes it's just obvious. You look at the equation and you say, oh, you know, e to the x will work, right, or something like this, or x times x plus 1 would work, or something. But it's not, at that point, it's art, right? It's like the difference between integration and differentiation, right? I mean, you know, when you differentiate, you can differentiate anything. When you integrate, you just have to see something, right? You have to figure it out. So with Riccati equations, well, of course, solving differential equations is integrating. So there, it's as non-trivial as taking integrals. Right, so now I've given you enough material so that you can start doing your first problem set, which you should start doing well ahead of its deadline. Which means that I can now spend a few, spend a few more minutes, or maybe tens of minutes, on continuing with a sort of an introduction to, you know, what I call the language, right? So I want to introduce a few more notions, because this is pretty much all the conversations that we can have in the language introduced so far, right? So we need to learn some more grammar to construct more complicated sentences. And so let's do that. So language part 2 of this. let me motivate this with a physics problem. This is one of the most famous, maybe the most famous physics problem of all time. It's a mathematical pendulum, right? Let's consider this. So point mass on a string, on a rigid string, with gravity pointing downwards, length L, and the equilibrium position is clearly when it's just hanging down, and this here is the angle of its deviation from equilibrium. And so what will it do? Well, it'll oscillate along the arc of a circle of radius L, right? So that seems clear. What's the equation for such a thing? What's Newton's law? Well, Newton's law is acceleration of motion along this arc, which is just L theta double dot, right? So, and the force is the projection of gravity onto this direction, right? And so this is minus mg sine theta. Okay, so that's the equation of pendulum. You've done this in mechanics, I hope, right? Maybe even in school, but certainly since. So I can rearrange this for the purposes of treating this as a mathematical equation as theta double dot equals to minus omega naught squared sine theta, where the frequency, omega naught, is square root of g over L. So this is called the equation of mathematical pendulum. Mathematical because massless, because the rod doesn't have a mass, because there's no friction, and so on. So it's an idealized Platonic absolute of a pendulum. So now let's remember I told you that in the vicinity of any given point, a nonlinear equation can be made linear. Right? Well, here's the first example of that, right? So this equation is clearly nonlinear. Sine theta is not a linear function, right? But I can say that in the vicinity of theta equals to 0, theta is small. So if I perturb my pendulum only slightly, I can expand the sign, and so theta double dot is simply minus omega naught squared times theta, right? And so this is called a simple harmonic oscillator, right? And again, this is probably something you've come across before. Simple harmonic oscillator, also known as SHO. A thing has an acronym, it's made it in the world, right? So this equation is, well, I said to you before that y dot equals to AY was the most important ordinary differential equation of all time. This is the second most important ordinary differential of all time, and actually probably the most important equation in physics, right? Because pretty much everything, well, not everything, but almost everything consists of things like this. Right. So let's see what. So this equation is. Why is this a new thing for you? Well, this is a second order equation, right? So there are two derivatives. So second order. So we're dealing with a somewhat new beast here. How do we deal with this new beast? Well, the solution to this equation. Again, I haven't yet taught you how to solve these things systematically, but you can verify this by substitution. It's some constant A cosine omega naught t plus phase phi. Right? So this is a solution, and you probably know this. Again, I could say, but do you know what a cosine is? Right? Well, a cosine, of course, by definition, is the solution of this equation. So again, all I've written is just shorthand for solution of SHO, right? So and you can construct the cosine as the solution to this equation, right? I kid you not. In fact, you have a homework where you can do that. Although it's extracurricular, I think it'll become curricular next year, I think. I mean, in the second year, in the mathematical methods, you do this all the time, these kinds of things all the time. So, right, so there are two constants, and there are now two constants, right, A and phi. That's because the equation is second order, but I haven't yet proven to you that there is this connection. The number of constants is equal to the order of the equation, but we'll see soon why that is. So, so these two can be fixed by initial conditions again, right? So if I were to tell you what the initial deviation of the pendulum from equilibrium was, and if I also were to tell you what its initial velocity was, that would fix the constants. Right. So that's an example of a second order equation, and of course this is a particular case of a very general equation, which is r vector double dot equals to some vector of t, r, and r dot. And this is the general form of laws of motion. Right? This is Newton's law in mathematical form. Right? Acceleration equals to force. Right? And that's why these kinds of equations are so dominant in physics. Right? The world, or at least the classical world, is described by this equation, or by equations in this form. So, well, you know the famous question, right? Is the world deterministic? Right? Is it? Can I predict what will happen with the world if I know the initial conditions? Well, that's a question of existence and uniqueness, right? Is there a Cauchy problem for such an equation whose solution exists and is unique? Well, I will tell you the answer to this question. Well, the answer is obviously yes, right? But I will discuss that answer in a moment. But first, let me point out the following important thing. All ordinary differential equations are first order ordinary differential equations, or systems thereof. How can this be? You might say, how second order equation is manifestly present on the board, and yet I say things like this. Well, this looks like a second order equation, but actually I could rewrite it like this. Right? So, equivalently, for example, for the simple harmonic oscillator, theta dot is equal to some omega, omega is equal to minus omega naught theta. Or I can even write it like this: d by dt theta omega is equal to matrix 0, 1 minus omega naught squared 0 dot theta omega. So you see, formally, any second order equation can be turned into a set of first order equations, but of course at the price of doubling the number of dimensions. Right? So more variables turns everything into having only one derivative. And so we can generally discuss equations in the form, so general ODE, therefore, is y dot equals to some vector f of t and y, where in that case y is r and v, right? So it's in 6 dimensions for the world, right? Or it could be in n dimensions or 2n dimensions and so on. So how do we turn the previous definition of the differential equation that I gave you, which was t f of t y y dot y to the n, right? So this was the old definition. And I said this is nth order. How do I now treat them in this form? Well, easy enough. I say that pi is equal to yi. So ith derivative of the function is going to be called p. And then my equation becomes f of t y p1 pn minus 1 pn equals to 0, equation number 1. Sorry, pn, what have I done? Pn minus 1 dot, right? So I do this for I running from 1 to n minus 1. And then I say that y dot is equal to p1, p1 dot is equal to p2, etc. pn minus 2 dot is equal to pn minus 1. And this is n equations, each of them first order. So anything that I care to think about in this course is in fact writable in this form. Okay? So let's see. Let's make a break for 7.5 minutes, and then we'll continue.